Now let us solve numerical 3. Again, it is also analyze numerical. So we are going to analyze the given compression number. Determine the design axial compressive load capacity of the column ISHB 300 at 58.8 kg per meter. If the length of column is 3 meter and its both the end are pinned. So let us write the given data. So given data is we have ISHB 300 Indian Standard Heavy Beam, that is nothing but ISHB. So it is the I section. Let me draw the I section. Okay, this is the I section. Since it is 300, the value is given as 300. That means the depth of the section is 300. Now this section is ISHB 300 at the rate of 58.8 kg upon meter. Now what is this value? So this is the weight of this I section. For per meter length, the weight of this I section is 58.8 kg. For single meter, it weighs 58.8 kg. And the length of the column is 3 meter. It is given here. And its end are pinned. So ends, both the ends are pinned. So you need to find out what is the effective length and also the property of this ISHB 300. So let's write down the property of ISHB 300 at 58.8 kg per meter. For this, you need to refer the steel tables. Now here is the I section, rolled steel beams, and if you look at this ISHB 300, and there are two ISHB 300. Okay, so which one is the one given in our numerical? Is we need to refer its weight. So one is 58.8, another one is 63. So this is the I section which has been given in our numerical. For this given I section, the area is 74.85 centimeter square. So let's note down the area. So area is 74.85 centimeter square. Let's convert this into mm. 7485 mm square. That is the area of given I section AE. Okay, then the depth of section is 300. It is clear that ISHB 300 has the depth 300 and width of flange B is equal to 250. So if you come back to this diagram, width of the flange given is 250 mm. This we will denote it by BF, width of the flange. The depth of the section is denoted by. Now thickness of the flange TF is 10.6 and the thickness of web is 7.8. So this is the flange. Thickness of flange is 10.6 mm and the thickness of web TW is 7.8 mm. Okay, this is the property. Apart from this, we need to note down what is the moment of inertia and the radius of gyration about xx and yy axis. So we have axis xx and axis yy. Can you guess which has the least moment of inertia? Which axis will buckle? Is it xx or yy? Yes, you can guess. It is simple. It is about the axis YY. That is where the minimum moment of inertia is, and that is where the buckling is gonna happen. So the strength in that axis is the strength of the given I section, because on the other axis strength is more. If you apply the load, whichever axis has the least strength, and if that reaches, then buckling will happen, the column failure will happen. So the strength is the least strength of both axis strength. So if you go back to the steel table, if you check the moment of inertia about the axis XX and YY, it is clear that YY has the least moment of inertia, that is 2193.6 centimeter power 4. So IYY is 2193.6 centimeter power 4. If you want to write in mm power 4, then 2193.6 into 10 to the power 4 mm power 4. 1 centimeter is 10 mm. So I am not going to write IXX here because it is always more than YY. So I'm not worried about the XX. So as far as column is concerned, we have to always think about the least value in moment of inertia and the least value in radius of gyration. And in radius of gyration as well, we have RXX, RYY. So RXX, radius of gyration about XX is 12.95 centimeter, and the radius of gyration about the axis YY is 5.41. So my concern is always the least value, 5.41. So Ry is 5.41 centimeter. If I want to write it in mm, then 54.1 mm. Okay, now I know all the value. I know minimum or least moment of inertia. I know least radius of gyration, and now I need to know what is the effective length. I know the total length is 3 meter. Ends are pinned. Now what is my effective length? Yeah, effective length of a given column. Now if you go back to table number 11 of IS 800 2007, the effective length of prismatic compression member is given here. So our end is pinned, and we have a pin in one end and also pin in the other end. So pinned is nothing but rotation is free. This point or this joint is allowed freely to rotate, but it is restrained against translation. So this end won't move, but it can rotate. So this is the pinned end. So if both ends are pinned, my effective length is 1 times the total length of column. So my effective length is 1 times the total length. So 1 time multiplied with 3000. So I'm writing it here in mm. So my effective length of given column is 3000 mm. So this is my effective length. Now I know every data. Now I need to find what is the design axial compressive load capacity. Now if we go back to the equation of the class 712, design compressive strength is equal to area into design compressive stress. Now FCD can be computed either by using this equation or by using table 9C. Again in table 9. In table 9 you have a 4 table, 9A, 9B, 9C and 9D. So all the table is corresponding to its buckling axis A, B, C and D. To know the buckling class, whether A, B, C or D, to know the buckling class of a given section, you need to refer table number 10 of IS 800 2007. Here for all the section it has been given, And our concern is about rolled steel I section because ours is I and rolled steel, not welded I section. So in the rolled steel I section, you need to check whether it falls, the given cross section falls in this criteria or in this criteria. Let's check it. First value is H by BF. Now my H by BF value, H is the depth of section, which is 300, and BF is the width of flange, which is 250. That is 1.2. Now let's go back to the table and let's check. Now H by BF is greater than 1.2. Then it falls under this criteria. So ours is exactly equal to 1.2. It is not greater than 1.2. Okay, now this criteria is not satisfied. Let's go back to this second criteria. Here, what is our H by BF? That is less than or equal to 1.2. Then you need to check this criteria. So if you go back to our value, which is exactly equal to 1.2, that means less than or equal to 1.2. So in this criteria, there are two. You need to check the thickness of flange. So what is our thickness of flange? Our thickness of flange TF is 10.6 mm. You can refer steel tables. For the given thickness of flange 10.6, whether which is less than or equal to 100 mm or greater than 100 mm. Obviously it is less than or equal to 100 mm. So it satisfies this criteria. Okay, for this criteria, the corresponding buckling axis. So you have buckling axis ZZ and YY. So again, let me draw I section in line sketch. This is my axis XX and this is my axis YY. So XX is given as a ZZ in this table. So whether my buckling is going to happen in ZZ or YY. So it is clear, we have seen in the given value from the steel table that moment of inertia about YY is the least, and also radius of gyration about YY is the least. So buckling is going to happen in the axis YY. So if buckling is going to happen in this axis YY, then the corresponding buckling class is C. So from this table C, we found out what is the buckling class for a given section. So buckling class for a given section is C. That means you need to refer table 9C to find design compressive stress FCD. Okay, here is the table 9C, design compressive stress FCD for the buckling class C. So whatever the value given in this table, it is all design compressive stress corresponding to the yield stress, which is 250 mild steel, and the value corresponding to given slenderness ratio. Now we need to find out what is our slenderness ratio. So let's find the slenderness ratio lambda. Slenderness ratio lambda, which is equal to L effective by R minimum. We know that our effective length of the column is 3000 mm and the minimum radius of gyration is 54.1 mm. So if you substitute, the slenderness ratio lambda is 55.45. Again it is not, again it is unitless. So whenever you calculate the slenderness ratio, you have to always make sure whether which is less than or equal to 180. If it is subjected, the compression member is subjected to dead load or imposed load, live load, or which is less than or equal to 250 if the compression member is subjected to earthquake or wind load. So in our case, since it is less than 180 or 250, so the given compression member is safe against buckling. Okay, now we know lambda, we know our stress is yield stress is 250 megapascal for a mild steel. Now let's go back to the table number. Now let's go back to table 9C. And Fy yield stress is 250 and the corresponding value for the slenderness ratio of 50 is 183 and for 60 it is 168. Let me write here the table. Here is the yield stress 250 Newton upon mm square and the slenderness ratio for 50 the design compressive stress is 183. For 60 the design compressive stress is 168. So for 55.45 the design compressive stress is how much? That by doing linear interpolation we'll be able to find. So FCD, which is 183 minus 183 minus 168 upon the difference multiplied with how much is from 50, 55.45, that is 5.45. So which will give the design compressive stress that is equal to 174.825 Newton upon mm square. See again, whenever you calculate design compressive stress, make sure that it is less than Fy by gamma m naught. Fy by gamma m naught is 227.27 megapascal. So it is less than the maximum permissible stress. Now the design compressive strength of a given number is area into design compressive stress. So area is 7485 mm square and design compressive stress is 174.825 Newton upon mm square. So the design compressive strength which I am getting is 1308.4 kilonewton. If you want, you can even calculate safe load. Safe load is the design compressive load upon load factor. So which is 872.26 kilonewton. Now this is the design and the safe compressive load of the given compression member. Thank you.